we will now continue with the fractionation of bitumen. In the earlier lectures, we have seen about the introduction related to the chemical composition of bitumen, where is information related to chemical composition used, what are the different scales in which it can be characterized. We saw the elemental level and the molecular level. So, in this lecture, we will be discussing about the fractionation techniques which are used to classify bitumen. So, what are this fractionation? Bitumen is now separated into different fractions. The separation can be based on precipitation or distillation or chromatographic analysis. So, we identify some property of this material and separate molecules which have identical property. In the previous lecture, we saw that we were separating molecules based on their molecular size and then we calculated the molecular weight. Here we are going to separate fractions based on their polarity. So, what do we mean by polarity? How reactive they are, how affinitive they are to a particular solvent. So, that is the parameter which is used here to separate fractions. And this separation of fractions based on polarity is very commonly used, and these solubility based techniques are relevant even today. There are different fractionation procedures which exist today, and we look at each of them. The first fractionation procedure is by Traxler and Squier in the year 1936. So, what is this fractionation procedure is, you take bitumen, we dissolve it in some particular solvent and then we allow it to precipitate. Whatever is the precipitate that we are getting here is called as asphaltics. So, you would have heard the term asphaltenes, right. So, that is the next version of this term asphaltics. Initially, this asphaltene fraction was referred as asphaltics. Further, it was coined as asphaltenes and that terminology is used even now. So, the insoluble fraction when it is mixed with the solvent is called as asphaltics, and whatever is the remaining part in the solution, that the butanol is evaporated. Here we have to see that N-butanol is used as a solvent. So, this solvent is evaporated and then the remaining material is dissolved in acetone. After dissolving it in acetone, it is chilled to minus 23 degree Celsius. After chilling it to minus 23 degree Celsius, whatever is precipitated is called as paraffinics. So, these paraffinics crystallize and hence they kind of precipitate when it is chilled to sub-zero temperatures. The remaining thing in the form of solution are called as cyclics. So, we have a procedure where we dissolve bitumen in a solvent, N-butanol is the solvent which is used here, and then whatever is precipitated initially we call it as asphaltics, and in the solution we evaporate the solvent, mix it with acetone and then we chill it to minus 23 degrees Celsius. So, whatever is precipitated in that case is called as paraffinics and the remaining are called cyclics. So, we have three fractions based on this procedure. So, this was the initial procedure which was given by Traxler and Squier in the year 1936. The next procedure, which is based on chemical precipitation, was given by Roasler and Sternberg in the year 1962. So, this was part of this particular standard ASTM D4124. So, here also we do identical kind of procedure. We take bitumen, we dissolve it in a particular solvent. So, here we can see N-pentane is used as a solvent. In the previous case, N-butane was used as a solvent. Here we are using N-pentane as a solvent. And after mixing bitumen in the solvent, whatever is precipitated is called as asphaltenes. The remaining part in the solution form is added with H2SO4 sulfuric acid at a concentration of 85%. So, after precipitating asphaltenes, the solution is added with sulfuric acid at a concentration of 85%. So, in that case, whatever is precipitated is called as nitrogen bases. Whatever is not precipitated again in the solution form is added with again sulfuric acid, but at a higher concentration 98%. So, then what is precipitated is called as first acidophene. After that, whatever is still remaining in the solution form is added with sulfuric acid and sulfur dioxide, and whatever is precipitated in this case is called as second acidophene. So, after doing all these things, whatever still remains in the solution form are called as paraffins. right. So, we have 5 fractions based on this particular procedure. Asphaltenes, again the precipitate, but whatever is in the solution form is classified differently. We have nitrogen bases, first acidophene, second acidophene and paraffins. We need to note that the asphaltics what we got in the previous case is not similar to the asphaltenes what we have seen here. It is just not with the name alone, but it depends upon the dissolving capacity of the solvent. In the previous case we used N-butanol as the solvent, but in this case we are using N-pentane as the solvent. So, as the number of carbon atoms increase, the solvent becomes more strong in nature. So, N-pentane is more strong in nature compared to N-butanol. So, this N-pentane can dissolve more number of insoluble fraction compared to N-butanol. So, the amount of asphaltene fraction that we are getting here and its properties are different in this procedure compared to the previous procedure. Next we have another procedure which was proposed by Corbett. It is called as Corbett fractionation procedure. It is based on an adsorption chromatographic technique. I will tell you what this technique is. We will be seeing in detail about this particular technique. But for now, let us look into this Corbett fractionation procedure. So, here we have this original asphalt, the bitumen, which is dissolved in N-heptane. So, we are using N-heptane as a solvent here. So, we can see that as the procedures come down, we are using stronger solvents here. Whatever is the insoluble, again it is called as asphaltene, similar to the previous cases. When you dissolve it in a solvent, the insoluble fraction which immediately kind of settle down are called as asphaltenes. So, these asphaltenes are higher molecular weight compounds and they try to easily separate out from the remaining fraction of bitumen. So, the insoluble fraction is called as asphaltenes. The soluble fraction is called as petrolanes. It is also called as maltenes. These petrolanes can also be called as maltenes. So, generally people divide the composition of bitumen into asphaltenes and maltenes or asphaltenes and petrolanes. Now, this petrolane fraction is subjected to an elution adsorption chromatography. Again, we will see what this is, just hold on it for a while. So, then N-heptane is first used as an eluent. So, we have seen that we are initially dissolving it in N-heptane. So, using the same solvent, mixing it with the solution and whatever is coming out are called as saturates. So, initial eluent is the N-heptane and then we are using benzene as an eluate. So, whatever is coming out is called as naphthene aromatics. Then we are using methanol benzene plus trichloroethylene as a solvent and then whatever is eluting is called as polar aromatics. So, here we are having 3 different fractions: saturates, naphthene aromatics and polar aromatics. So, initially N-heptane is used as a solvent and whatever is removed it is called as saturates. Then benzene is used as a solvent and whatever is removed is called as naphthene aromatics. Finally, a higher concentration solution, methanol benzene and trichloroethylene is used, right. So, this is the original fractionation procedure which was proposed by Corbett. This was later revised into an ASTM standard. So, we have this standard ASTM D4124. This is based on the Corbett procedure. So, here again it is kind of identical. We have asphalt, we are using N-heptane as a solvent, we are dissolving in it, whatever is precipitated is called as asphaltenes and whatever is in a solution form we call it as petrolanes, or here they have defined it as maltenes. It is then subjected to adsorption elution chromatography on alumina. So, here alumina is used as a chromatographic column. So, they have specified the material also. So, in the first cut N-heptane is used as a solvent and whatever we get initially is saturates, then toluene is used as a solvent, whatever we get is naphthene aromatics. Finally, methanol, toluene and trichloroethylene is used as a solvent. So, here they have specified methanol, toluene is 50% and trichloroethylene is 50%. So, in the previous case we see they have used benzene as a solvent here. So, due to the hazardous nature of benzene, benzene is restricted from using in laboratory and that was replaced by toluene. So, that is the major difference between the original Corbett procedure and the procedure which is given in ASTM D4124. There is something which is very important when you read ASTM D4124. They say that there is nothing called as a repeatability for this kind of procedure, because we know that bitumen is heterogeneous, but it kind of forms a homogeneous material, right. So, because of that, if we take a sample and then do this procedure on one material, we will get some results. If we are repeating the same procedure on another sample, it is not necessary that we need to get exactly the same numbers. There will be some variability because this procedure is not a particular standardized procedure. It works on adsorption chromatography. So, when we see how this adsorption chromatography works, then we will understand why we will not get repeatable results for two kind of specimens of the same material. So, this is how an adsorption chromatography works. It is also called as a thin layer chromatography. So, what is this thin layer chromatography? It is used to separate constituents in a mixture, right. So, we have a mixture of, we said that we have a mixture of 4 different materials. Let us just stick on to the Corbett procedure now. We have 4 fractions here. What are they? Asphaltenes, naphthene aromatics, polar aromatics and saturates. So, we have 4 fractions. Now, we need to separate these 4 fractions, right. So, for that we use an adsorption chromatography. So, here we have 2 phases, a stationary phase and a mobile phase. So, this column which is present here is a stationary phase. And we also have a mobile phase which is this solvent here, right. The solvents are separated based on their affinity towards the solvent phase or the mobile phase. So, that is the basic principle which is used in this particular procedure to separate fractions. So, what happens here is the solvent is placed as a spot here. So, we have the stationary phase. So, at the bottom of the stationary phase, we have the solvent which is placed as a spot. Now, we have the sample which is placed as a spot, and then we have a solvent which is filled here. The blue color one what we see here, right, that is the solvent. Now, this solvent tries to rise up this chromatographic column because of capillary action. So, when this tries to move up this chromatographic column, it dissolves this sample and it tries to carry this sample along as it moves up the chromatographic column. Now, how is mixture separated in this case? So, we said that the different components of this mixture can have different affinities towards the stationary phase and towards the mobile phase. Now, if this one component of this mixture has more affinity towards the solvent phase, it will try to move along with the solvent up the chromatographic column, whereas another component can have relatively lesser affinity towards the solvent and more affinity towards the stationary phase. So, in that case, it will rise up only slowly in the chromatographic column. So, you can see here it has 2 components. This sample spot which is in purple color has 2 components here. One is component A and the other one is component B. So, we can see that they start rising at different rates in the chromatographic column. So, this one in blue color has more affinity towards the solvent which is the mobile phase, whereas the one in red color has more affinity towards the stationary phase which is the alumina column which is used here. So, depending upon the relative affinity of the different components, they rise up the chromatographic column at different rates, and by this process we will be able to separate out different fractions. So, here in this third image, step 3, you can see it clearly. The one in blue color has risen up, whereas the other one is still remaining at a lower level. So, this will be eluted out of the chromatographic column initially, but this will happen at a later time. So, at time interval, we will be getting components at different time interval. So, by this manner, we can separate out the fractions. So, this is the principle which is used in the Corbett procedure to separate out all the 4 fractions. or the 3 fractions in fact, because the asphaltene fraction is initially precipitated out separately. So, only to separate the saturates, naphthene aromatics and polar aromatics, we are using this adsorption chromatography. Now, we have asphaltenes in all these 3 procedures. We have asphaltenes from the Traxler and Squier process, we have asphaltenes from the Roasler and Sternberg process, we also have asphaltenes from the Corbett process or the ASTM D4124 procedure. Now, can I compare all the 4 asphaltenes? I said initially, right, we cannot make such comparison because it depends upon the strength of the solvent to dissolve the components in bitumen. So, we said N-heptane is has higher strength to dissolve the components. So, the amount of asphaltene fraction here will be very less compared to the use of N-pentane. So, the amount of asphaltene we get in the case of N-butanol as a solvent will be high compared to the percentage of asphaltene we get when you use N-heptane as a solvent. So, this study by Goodridge et al. Compares the different fractions from 2 different procedures. So, we see that the first one is ASTM D4124 based on the Corbett procedure and the second one is D2006 based on the Roasler procedure. You can see how again the fractions are different, right. In Roasler we defined 5 fractions, in Corbett we have 4 fractions. So, again the fractions are going to be different. Let us just compare the asphaltene fraction alone. Like I mentioned earlier, the amount of asphaltene fraction in the Corbett procedure is relatively lower compared to that what we get from the Roasler procedure. So, this is because here we use N-heptane as the solvent, whereas here N-pentane is used as the solvent. So, depending upon that we will get different fractions. So, the ultimate point which we are trying to convey here is different fractionation procedures use different solvents and the procedures are completely different. So, all of these fractions are completely solubility based. So, how much this particular fraction can dissolve in a particular solvent. So, if I change the solvent, the affinity is going to change. So, my proportions will be completely different. So, only when I use a particular solvent based on a particular procedure, then we will be able to compare these fractions of 2 different materials. So, if I use the standard Corbett procedure given in ASTM D4124 using N-heptane as a solvent and all the other solvents which were described earlier, then I can compare the 4 fractions from 2 different materials. If I change the solvent or any of the steps which is given in the procedure, then I will not be able to compare across these different fractions obtained for 2 different samples. So, this we need to keep in mind when we are looking into these fractions for different samples. It is very convenient to represent the chemical composition of bitumen using these fractions. Even now, people prefer this as a very convenient method to represent the change in chemical composition of 2 different samples. But when we do that, we need to make sure on what procedure these fractions were evaluated. Next, we will define what are these 4 fractions, because the Corbett procedure is what is commonly used and we said we have 4 fractions. So, let us just see at the molecular level what these 4 fractions are composed of. Let us begin with saturates. They are composed of alkanes, right. By this time we know what these alkanes are. They are linear long chain compounds. We also have cycloalkanes. So, we said again, right, they form into cyclic structures but without an inner ring core and also their mixture, right. Again, this is a hypothetical structure which was given by Masson et al. We can see they are composed of mostly linear long chain, but they also have some amount of aromatic content which is present here. They constitute about 5 to 20% of the composition of bitumen and the molecular weight here ranges from 470 to 880 gram per mole. This is again a range. It can vary from one end to another depending upon the type of bitumen we use. So, this is the first fraction. Saturates, which are only linear compounds, we can see there are no heteroatoms here, no carbon, no nitrogen, no oxygen. So, none of these, again no sulfur, no nitrogen, no oxygen, no sulfur. None of these elements are present in this particular fraction. Next, we will move on to the next fraction, which is naphthene aromatics. These naphthene aromatics are a mixture of alkanes, naphthenes and aromatics. Again these naphthenes are nothing but cyclics, right. So, they also are composed of alkanes, naphthenes and aromatics, but they have more proportion of alkanes compared to these two fractions.
And they constitute about 40 to 65% of the composition in bitumen.
And the molecular weight here ranges from 570 to 980 gram per mole. So, you can see this again hypothetical structure of a naphthene aromatic. We can see it is composed of some alkanes. It also has some amount of naphthenes, it also has aromatics, it has some amount of heteroatoms also. You can see oxygen and sulfur present here, very small percentages compared to the other two fractions, polar aromatics and asphaltenes. So, this is the composition of naphthene aromatics. These polar aromatics are again a mixture of alkanes, naphthenes and aromatics. Similar to the previous case. The previous case also we defined only these three. So, here also it is composed of these three compounds, but then the naphthenes and aromatics are present in higher percentages. So, this is present in higher percentage compared to alkenes, and they constitute about 30 to 45% of the composition. Again here the molecular weight ranges from 780 to 1400 gram per mole. If you look at this structure, we can see they have more amount of aromatics which is present here, all these rings which we can see here, right. They have more amount of aromatics, they also have alkanes, they also have heteroatoms, and you can see the molecules tend to get bigger, right. So, these are the polar aromatics fraction, and finally the asphaltene fraction. So, these asphaltenes are polynuclear aromatics with alkyl substitution. So, it is like they are a very big molecule, not with a single nucleus, but they have many nucleus. So, that is what is called as a polynuclear aromatic with alkyl substitution. So, they have some alkyl chains which are present here, and they constitute about 5 to 25% of composition. When you look at different crudes or chemical composition techniques on bitumen, people usually tend to separate out asphaltenes and study asphaltenes in detail, because these are the higher molecular weight compounds and people believe that they tend to influence the physical properties more compared to the other three fractions. That is one reason. The other reason is these asphaltenes can be easily separated out, because we dissolve it in a solvent, whatever is precipitated is called as asphaltenes. So, it is easy to separate out this fraction. So, because of these two reasons, asphaltene is one of the most commonly studied component of bitumen, and we can see the molecular weight here ranges from 800 to 3500. So, they are really big molecules. So, this is the chemical composition of all these four fractions which are present in bitumen. Again, all of them are hypothetical. People have some measurements in relation to all of them, but nobody has any verified structure for each of this fraction. So, in summary, we will see bitumen has saturates. We have seen what they are: naphthene aromatics, polar aromatics and asphaltenes. We can see how the size of the molecule increases from saturates to asphaltenes. This is a study in which they have said what is the percentage of carbon, hydrogen, nitrogen, sulfur, oxygen and this hydrocarbon ratio in these four fractions. So, we have asphaltenes, they are specific here, asphaltenes which are insoluble in N-heptane as a solvent. So, this is called as N-heptane asphaltenes. That is how they define N-heptane asphaltene, N-pentane asphaltene, specifying what is the solvent which is used here. And they have also said resins. These resins are nothing but the polar aromatics fraction. So, these polar aromatic fraction in some literature is also referred as resins. So, this comes from crude oil literature where they have SARA fraction. Saturates, aromatics, resins, asphaltenes, right, similar to saturates, naphthene aromatics, polar aromatics and asphaltenes. Again the fractions are similar, but we have to mind what is the solvent and what is the procedure which is used in both the cases. Now, if we see what is their percentage contribution on the whole bitumen, we can see asphaltenes are present only as 5%, right? Only 5% of the whole bitumen is composed of asphaltenes. We have resins about 20%, we have aromatics about 60% and saturates as 10%. So, this is the contribution. Again, this is specific to this particular study. When we have different type of bitumen, this can vary over a range. And we see what is the carbon which is present here, the percentage weight of carbon. The asphaltenes have 82% carbon, resins 81, aromatics 83 and saturates have higher percentage of carbon. About 85% of carbon is present in the saturates fraction. And when you look at hydrogen, the amount of hydrogen is very less in the case of asphaltenes, whereas it is high in the case of saturates. So, previously we said, right, the number of hydrogen atom is less in a bigger molecule because one bond is always taken by one or many bonds are taken by a carbon atom. So, in a big molecule, the amount of hydrogen atoms are lesser. So, when we look at this hydrocarbon ratio, it keeps increasing. For materials with larger molecules, lesser hydrogen content, the hydrocarbon ratio is lesser, whereas in the case of saturates fraction, we can see this hydrocarbon ratio is about 1.8. Now, let us look at the heteroatoms. We see that nitrogen is about 1% in the case of asphaltenes and resins, 0.1% in the case of aromatics and 0.05% in the case of saturates. So, we said these saturates fraction may have very small amount of traces or may not have any of these heteroatoms at all. So, like we said, the heteroatom nitrogen content keeps decreasing as we move from asphaltenes to saturates. The next fraction is sulfur. Again in sulfur we can see the sulfur content reduces as we move from asphaltenes to saturates. The oxygen content they were observed only in the asphaltene fraction, and in this study they did not observe oxygen in the remaining 3 fractions. So, these asphaltene as proposed has more number of heteroatoms and they seem to have bigger molecules. So, only based on some understanding like this, people tend to propose hypothetical structures for all these 4 fractions. So, these 2 Corbett fractions are widely used to represent the microstructure of bitumen. But there is something which we have to remember here. There was a study which was conducted by Harrison et al. As part of an SHRP program. So, they had measured DSC on bitumen and each of these 4 fractions. I will tell you what DSC is in a while. So, you just remember that it captures the thermal events in bitumen. So, they tried to capture the thermal events in bitumen as a whole and each of these 4 fractions of bitumen. But when they put together the information on each of these 4 fractions, they did not get the thermal events for the whole bitumen. So, then people started saying that the interactions between these 4 fractions are also important and they are lost when we separate them into fractions. So, the affinity of one fraction to other and the interactions which arise due to them is lost when the fractionation is done. So, that is the reason why we are not able to see a whole response when we sum up the response of the individual fractions. So, that is something we need to take in mind. But again, irrespective of this factor, people still prefer this fractionation procedure to represent the chemical composition.